Okay, so next I want to discuss some more analysis, go into more depth into some analysis of ridge regression, similar to the analysis that I did for least squares. So the solution to least squares and ridge regression are clearly very similar. Here on the left we see the least squares solution that we've been discussing, and on the right we see the ridge regression solution. The only difference is in this additional term here, lambda. And so let's discuss what this lambda is doing in a bit more detail. And so the way that we can compare these two are using properties of using techniques from linear algebra and also from probability in order to better understand what ridge regression is doing and how it relates and compares to what least squares is doing. So the way that we're going to do this is using something called the singular value decomposition. And so let's quickly go through a one-slide review of the singular value decomposition. So we know that we can write any n by d matrix X where we're assuming that n is greater than d, so we have more observations than dimensions in our problem, as this matrix product U S times V transpose, where these are all three matrices. U is an n by d matrix. We assume that it's orthonormal in the columns. What this means is that U transpose U is the identity matrix. So each column of U is unit length and is orthogonal to every other column in that same matrix. The matrix S is a d by d non-negative diagonal matrix. So the ith value along the diagonal of S is non-negative. It can be 0. And the off-diagonal values are all equal to 0. And the matrix V is d by d and orthonormal. And so because it's square, we can say that V transpose V is also equal to V transpose. And both of those are equal to the identity matrix. So the columns of V are orthonormal, and the rows of V are also orthonormal. Okay, so from this we have some immediate equalities. We have, if we have X transpose X, which is of interest because it's in both the least squares and the ridge regression solution. So we have X transpose X is equal to this matrix product, where we're simply replacing the singular value decomposition for X. And then because we use the property that the transpose of a matrix product is equal to the transpose of each individual matrix in reverse order. So we get U transpose times U here, which cancels out because of the assumption, because we're using a singular value decomposition. We have S transpose, which is S, because it's diagonal, times S, so we have S squared. And then on the outside of this, we have V transpose, which is just V, and then V transpose on the right. So this matrix product is equal to this. And similarly, XX transpose is equal to U S squared U transpose. So if we assume that the matrix X is full rank, meaning that all diagonal elements of the matrix S are strictly non-negative, are greater than 0, then we also can write the inverse of X transpose X as follows. So we know X transpose X is equal to V S squared V transpose. The inverse of a matrix is of a matrix with this form, where V is a square orthonormal matrix, is simply taking the diagonal middle matrix and inverting it. And if you want a quick proof of that, you simply can take X transpose X times its inverse and replace that with its singular value decomposition and find that you get the identity matrix. So that's how you can show that the inverse is equal to Vs to the negative 2 V transpose. Okay, so let's use the SVD to analyze the least square solution. So when we looked at the variance of the least square solution, we saw that it was equal to this matrix, sigma squared times the inverse of X transpose X. We now replace X transpose X inverse with what we obtained from its singular value decomposition. And we notice that this inverse of S is going to become huge when we have singular values that are very, very small. So when the matrix X has singular values that are close to 0, when we square that, they become even closer to 0 if those values are less than 1. And then when we invert that, we have very large values in this diagonal matrix. And so we can say that the matrix, that the least square solution is not going to be stable when the singular values of the matrix X, when there are some singular values that are small. And so this is something that we can actually calculate because we have the matrix X. It's part of our data set. So we can construct it. We can, in our favorite coding platform, call the singular value decomposition function to get its singular values and look at them and see, are there singular values that are close to 0? If there are, then there's a good chance that our solution to the least squares problem is not going to be stable. It's going to have values that aren't close to the ground truth. And so when does something like this happen? Intuitively, we can think of when there are columns of the matrix X that are very highly correlated with each other, then we're going to have singular values that are very small. So, for example, we might think that we're making many measurements of our data, and we're returning these high-dimensional vectors X that are going to give us many things to help predict the output. But if the different dimensions of those measurements are very highly correlated, then we're not actually helping ourselves solve the problem. So if we want to see how having small singular values are going to affect our prediction, we can simply look at how we make predictions for least squares. We take our new vector X, the dot product with our least square solution, and say that that's our prediction of the corresponding response or output. If we replace the least square solution with the singular value representation, we can see that when there are small singular values, the inverse of that matrix of singular values will be very huge, and depending on the value of the vector X, we could also have predictions that are wide off the mark, depending on how the vector X correlates with those singular vectors that have corresponding small singular values. Okay, so in the next few slides, I want to look more closely at the relationship, the mathematical relationship between ridge regression and least squares. So first, let's recall that if we have two symmetric matrices, A and B, they're both symmetric matrices, then the inverse of A times B can be calculated by taking the inverse of each of those matrices separately and then reversing the order. So AB inverse is equal to B inverse times A inverse. So now if we want to look at the ridge regression solution, let's kind of work through it and manipulate it in a certain way to relate it to the least squares solution. So here in the first row, we have the ridge regression solution. This is what we solved on a previous slide. Now let's do something a bit simplistic, and let's multiply and divide by the same thing. So let's wedge in this part here, the matrix X transpose X times the inverse of X transpose X. So this matrix product is the identity, and so we haven't actually changed the solution by going from the first line to the second line by adding a matrix times the inverse of itself. However, now we can look at this matrix vector product and recognize this as the least squares solution. So let's write, instead of writing it in long form, let's just simply replace that with WLS, the least squares solution. Similarly here, let's do something a bit simplistic and write this lambda inverse, lambda times the identity plus X transpose X as a product of X transpose X, that matrix, by the matrix lambda times X transpose inverse times the plus the identity. So if we multiply through X transpose X, multiply that through this term here, we see that this term is simply equal to this term. However, here's where we're going to use the property at the top, where the inverse of these two symmetric matrices multiplied with each other is equal to the inverse of this matrix times the inverse of this matrix. And so that's what I've written here. The inverse of this second matrix, which is a symmetric matrix, times the inverse of the first matrix, which is also a symmetric matrix, is equal to the inverse of the product of those two matrices. But now doing this, we notice that these two matrices cancel out. And we're finally left with this relationship, that the ridge regression solution is equal to a matrix times the least squares solution. So they stand in this very specific relationship to each other, where we take the least squares solution and we multiply it by whatever this matrix turns out to be. It's calculated using things that we know, so we can calculate it. And we can simply manipulate the least squares solution according to this vector in order to get the ridge regression solution. And so immediately we can see that we should be able to expect the ridge regression solution to have smaller magnitude than the least squares solution. This is the identity. And then we're adding something that's non-negative to it, that has non-negative singular values. And so you can imagine this is dividing by something greater than 1. So we're going to be shrinking this. So I'll discuss this more specifically in a moment. Okay, so let's now continue this line of analysis, where we're now going to replace the matrix X by its singular value decomposition. And so again, we can write a matrix X as a product of these three matrices that have the properties discussed on the previous slide. And therefore, this matrix X transpose X inverse can be written in this way. And so now, if we continue from the previous slide, where this first line is the last line of the previous slide, and now replace this matrix X transpose X inverse by the matrices that we obtain from the singular value decomposition of X, we get this sequence. So we get this term by replacing this matrix with this matrix. And now, because V is a square orthonormal matrix, and because I and lambda S inverse squared are both diagonal matrices, because those two things are true, we can write this matrix in this way. And so we can simply pull out the V's on both sides and then invert this matrix lambda S inverse squared plus the identity. If we want to prove why that's true, simply multiply this matrix by the matrix that we obtain from the term in between the brackets, and notice that the result is the identity matrix, and that's how you can show that's true. Okay, so now let's call this inner matrix here M. Let's just define M to be equal to the identity plus lambda sigma inverse squared. And then if we do that, we notice that M is a diagonal matrix, and the ith value on the diagonal of M is equal to the ith singular value squared divided by lambda plus the ith singular value squared. So we get a matrix M that has diagonal values like this. And now let's take the solution of least squares and also use the singular value decomposition of X, and we'll be able to show in a straightforward way that the least squares solution can be written in this way, where U, S, and V are calculated from the singular value decomposition of X. So this is something that you could show very easily. And then we see that the ridge regression solution, knowing that it's equal to VM V transpose times the least squares solution, which is equal to this, plugging all of those things together in, we find that the ridge regression solution can be written in this way. V times a matrix that we define, S lambda inverse, times U transpose times Y. U and V are both the leftmost and rightmost matrices of the singular value decomposition of X. S lambda inverse is calculated in this way. It's equal to essentially M, where the numerator is now doesn't have the squared term. So S lambda inverse is equal to a diagonal matrix where the ith value along the diagonal is equal to the ith singular value divided by lambda plus the ith singular value squared. And so remember that as lambda goes to 0, we get the least squares solution back. And so we can kind of see from this matrix what's going on. Imagine that the dth singular value is extremely small. It's very close to 0. Then when lambda is equal to 0, we have that this term is 1 divided by the dth singular value, which is a massive number, which was the issue that we were running into previously. By adding lambda, we essentially put a floor on that. So as the singular value decomposition, as the singular values go to 0, for a lambda greater than 0, this term actually goes to 0 instead of infinity. When lambda is equal to 0, as SDD goes to 0, this term goes to infinity. But now if lambda is greater than 0, then this term goes to 0 as SDD goes to 0, because this lambda is kind of putting a floor on the smallest value that this denominator can take. So lambda is essentially killing off these small singular values. And so here's a mathematical way that we can understand exactly how it's doing that. So the third relationship I want to look at briefly is how ridge regression relates to least squares as a least squares problem. So we can actually write ridge regression as a special case of least squares. And to do this, what we do is we take the original problem where we say that y, the vector of all the responses, the n-dimensional vector y, is approximately equal to the matrix X that we construct by putting the inputs along the rows of X, times the vector W. And then we extend this problem by adding D or D plus 1 more terms to it. So I'll assume that we've standardized our data so we don't have the dimension of 1s. I'll assume that we're just simply looking at a D column matrix here. And so if we take the original y and then we attach D zeros, extend it by D dimensions and put 0 below it, and then take the matrix X and extend it by D dimensions along the first dimension, and then attach a diagonal matrix at the bottom of X that has the value, the square root of lambda along the diagonal, and then solve the least squares solution for W for this problem. So what we're calling this vector is y hat. We'll call this matrix x hat, and then W is left unchanged. And then solve the least squares solution to the problem y hat minus x hat W transpose times itself. So the sum of squared errors of this problem. Then if we multiply that all through, what we find is that we're equivalently trying to minimize over W this term, which is, if we rewrite it in another way, simply the original ridge regression term. So in a sense, ridge regression is almost like an augmented least squares problem.